Dear friends, today we have with us a very eminent scientist, Dr. Yashwant Gupta, who is the director of National Center for Radio Astrophysics in India. He is also involved with the Square Kilometre Array Telescope project, which is a collaboration between Australia, India, and several other countries. Dr. Yashwant Gupta, thank you so much for joining the Australia today.
Thank you, and it's my pleasure to be here.
Yeah. Dr. Gupta, let us first begin by a discovery which has been made by GMRT, which stands for the Giant Metrewave Radio Telescope, which comes under the NCRA umbrella. What is this discovery about, and how is it significant?
Yeah, so thank you for bringing attention to the latest new discovery from the GMRT. The GMRT studies various objects, and out of these are what are called radio galaxies. And often, radio galaxies occur in large clusters in the universe. And In these clusters, you can find galaxies which are active, which are undergoing energy release in the form of radio waves and signals, and then you can find galaxies which were active at some point of time but are no longer active. So you could think of them as dead galaxies, and when you think of dead creatures or organisms, you think of fossils that you can
Yeah.
then find evidence from them only by finding the fossilized remains rather than finding the live object. So, in that analogy, it is interesting to find such fossil radio galaxies, and they're often found most easily inside such clusters because there's a mechanism in the cluster whereby you can sort of throw light on fossil galaxies. And In this particular case, the team, which is led by a colleague from the Pune University, which is right next doors to where we are, have made this discovery where they have detected uh, what is currently to date the oldest known such fossil. So it's similar when you go look for dinosaur fossils and you find the oldest dinosaur, then you've made one of the most important discoveries because then you say, well, this is how long ago they lived, right?
Yeah.
So in the same way, when you can find the oldest of these, then you can trace back the history of that cluster of galaxies and study and understand the physics of it much better. So that, in a nutshell, is this new discovery and its importance, and the fact that it was made using primarily the data from the GMRT by a team which has been very active in this area is makes it all very interesting.
Yeah, and this is not the first significant and important discovery by GMRT. I mean, it's made several very important and significant discoveries in the past. One being, I think, in 2018, where it discovered the oldest known radio galaxy in the universe, which was found to be around estimated to be around 12 billion light years away. So, could you throw some light on that discovery and maybe a few others of significance in the last couple of years?
Yes, sure. So, just like finding these fossil radio galaxies is interesting, and to find the oldest ones. In the same way, if you want to understand the history of the universe from the early days as to how it evolved after the Big Bang, it's very important to go and find the oldest of the stars and galaxies that you can detect in the universe. And of course, you can do this with at different parts of the electromagnetic spectrum. And in radio, again, it's important to see which is the farthest of these radio galaxies that you can detect and what properties do they have. It tells you about what was the state of the universe at that time in its evolution, and it helps you to reconstruct the history of the evolution of the universe. So in this particular case, again, at this time it was an international team with astronomers from Leiden University in the Netherlands, and I think colleagues from Brazil, United Kingdom, Italy, and other places who used the GMRT to detect this one of the most distant radio galaxies ever known, located at a distance of about 12 billion light years. And so this is the time when the universe was about somewhere around 7 to 8% of its current age. And so it really, is telling you about the universe when it was in its youth, in the early days. And that's very useful to understand how the universe could be evolving. So that's the importance of that discovery. Similarly, there are various other signals that one wants to detect. So, the other important thing that one wants to know in the evolution of the universe is
Mhm.
how the amount of neutral hydrogen gas in the universe, in the galaxies, has evolved. I
Yeah.
think it's important to understand that the universe is largely made up of hydrogen gas. It's something we find a bit hard to understand when we look around us and say, look, there are so many different elements that
Mhm.
we are made up of, and the Earth has. But when
Mhm.
you look on the large scales of the universe,
Mhm.
the most predominant element is hydrogen, the
Mhm.
simplest of the elements. And it's found in all the galaxies. And if you can trace, and because that's the source of, how stars form and how planets form and how we evolve from that stage. So it's important to understand the history of the neutral hydrogen gas in the universe over cosmic time, as to, did galaxies always have the same amount of neutral hydrogen and therefore forming the same rate of stars formation, or was it different in the early days? If so, when did it peak, and so on? And
Mhm.
this is an important area of study, and many radio telescopes have been trying to see as to how far back can they look in
Mhm.
terms of detecting uh, the neutral hydrogen emission from the gas in galaxies. And in this particular case, about a couple of years ago, I think it was in 2020, in 2021, when the astronomers from NCRA and some colleagues from the Raman Research Institute in Bangalore, India, reported a brand new and very interesting result where they detected neutral hydrogen in emission from galaxies 8 billion years ago. Okay. Now, this is not
Okay.
as large as the 12 billion years ago that we saw for the furthest known radio galaxy, but this is
Mhm.
the furthest known detection of neutral hydrogen gas in the galaxies. And this again gives an important clue about the evolution of galaxies, as to in that era, did they have enough hydrogen gas to form stars,
Mhm.
and if and when did they run out of sufficient hydrogen gas? What happened? How did the galaxies evolve over time?
Mhm.
So that's another very interesting, relatively recent discovery with the GMRT. Similarly,
Yeah.
the GMRT has produced results in many other areas of science. It has been used to follow up what are called gamma ray bursts. So, gamma ray bursts are some of the most interesting and enigmatic transient events in the universe, where there is a
Mhm.
sudden burst that takes place. It's first seen in gamma rays, and that's why they're called gamma ray bursts. But with time, that is over days to weeks to months, you can see the radiation at radio waves. So these are large explosive events, and when you pick up the signal in the radio waves, you can follow it for many weeks to months. And that tells you the evolution of this explosive event that took place in some distant galaxy. And it helps you to understand the physics of the progenitor object, which was the original source which went through this cataclysmic kind of event. So there
Mhm.
are many such results from the GMRT in that area of work. Similarly, GMRT has also been very active in studying what are called pulsars.
Mm.
Pulsars are rapidly rotating neutron stars, which
Sure.
are very interesting objects. So it's a star which has as much mass as our sun, but
Mm.
condensed into a 10-kilometer size ball. So,
Mhm.
it's as much material as a sun collapsed into size smaller than a city.
Mhm.
And these are rotating very rapidly. They emit very energetic radio beams,
Mhm.
which you can see as the neutron star revolves and goes around. You see a beam, just like a lighthouse, and gives you a
Mhm.
beam every time the lighthouse rotates. And you can use these to study various properties of the neutron star itself. You can use this to study various properties of the interstellar medium between us and the neutron star. You can use it to study many more interesting aspects of physics, including probing Einstein's theories to the furthest limits, relativity, and trying to understand whether they work accurately in these regimes of, where the binary object around the neutron star is emitting. You can trace the history of evolution of binary stars and understand that. You can also use it to detect the passage of gravitational waves through a galaxy. So, in many of these areas, the GMRT has been making many useful and interesting contributions. The GMRT was also used a few years ago to make a large all sky survey
Mhm.
at 150 megahertz, which was called the TFR GMRT All Sky Survey. And it
Mhm.
is, like making an atlas. So when you make an atlas, you present everything that you know in a uniform manner about the entire Earth. In the same way, you try to cover as much of the universe as you can see from your observatory in a uniform manner, and you produce an atlas of what all you were able to detect. And this is very useful for people, just like an atlas is a very good reference material for doing various kinds of studies.
Mhm.
Astronomers use such surveys for as a reference material for various kinds of follow-up studies that they may be interested in different topics. So there's a
That's
whole range
wonderful.
of such different things that the GMRT has been doing over the 20 years or so that is it has been in operation.
Yeah. Dr. Gupta, leading on from those, what is the difference between a radio telescope and an optical telescope? And can you tell us a bit more about GMRT? Because I think this is the biggest such radio telescope in the world, if I remember correctly.
Yes. So, optical telescopes and radio telescopes are quite different, and in some cases complementary. So, as you know, that the electromagnetic spectrum spans a very wide range, all the way from the highest frequency gamma rays down through X-rays to ultraviolet to visible light to infrared, and then the lowest frequency is radio waves. And different objects in the universe emit at these different wavelengths based on the physics of what is happening. And uh, you can detect these signals by telescopes which operate in these specific parts of the electromagnetic spectrum. So, optical telescopes are the ones that pick up the signals in the optical part of the spectrum, and radio telescopes are the ones that pick up these lowest frequency electromagnetic signals in the radio part of the spectrum. And what happens is that you can get two kinds of results when you look at data from, say, an optical telescope and a radio telescope. Some objects which will emit both in radio and in optical, but you will get complementary information by looking at the data from radio and optical. Then there are some objects which will emit only in radio. So the example that I gave earlier about pulsars, they are objects which emit predominantly in the radio spectrum. They are hardly visible in the optical, for example. So if you did not have radio telescopes, you may not even have discovered these objects at all, or if so, maybe with great difficulty. And certainly, you would not be able to get the detailed information about what these objects are if you did not have radio telescopes. So there is both complementarity as well as exclusive things that radio telescopes can do. Now, of course, they are very different in their design and in their construction and the details of how they work. So, radio telescopes, in basically, they are like your satellite dish antenna, which picks up signals from a satellite dish and gives you your content, whether it's TV channels or it's other kinds of information. Except that they are looking at signals which are much, much fainter than the man-made radio signals that we get, with which we communicate and share information. And therefore, they need to be much bigger and to be sensitive enough to detect these faint signals that we get. So, in fact, often the radio telescopes are antennas which are several tens of meters, up to 100 meters, or even sometimes a bit larger than that in size.
Mm-hmm.
And furthermore, often they are arrays of such antennas. So the GMRT is, you can see the picture in my background, which shows these dish antennas. Each of these is 45 meters in diameter, which is quite
Mm-hmm.
large, and they're fully steerable. So you can move them in different directions to look
Okay.
at different objects in the sky, and you
Mm-hmm.
can steer the antenna as the Earth rotates. You can follow the object and keep observing it for long durations. And the array is spread out over a region of 30 kilometers.
Wow.
And that is done in order to get a high resolution, angular resolution in the sky. The signals from all the 30 antennas are brought over optical fiber to a common place in the central receiver room, where a
Mm-hmm.
lot of sophisticated electronics is there to process them. There's also sophisticated electronics at each antenna at the focus when the signal is first picked up and amplified, to get it to a level where it is easy to further transmit and handle. And
Mm-hmm.
so there is a lot of technology in radio observatory, all the way from mechanical engineering to servo engineering to radio frequency electronics to optical fiber, digital technology, and then a lot of software and data analysis techniques to
Mm-hmm.
understand the data, because the data volumes that are generated are quite large from an array of large antennas,
Mm-hmm.
and you need sophisticated analysis tools in order to make sense of the data and get the final results that the astronomer is interested in.
Yeah.
So that's the sort of the broad view of how radio telescopes work.
Yeah. Dr. Gupta, now coming to the Square Kilometre Array project, tell us a bit about that. And there's a collaboration between India, Australia, and a host of other countries. So tell us a bit more about that project.
Right. So the Square Kilometre Array is truly a next generation facility that is planned to be much more sensitive than any of the existing radio telescopes. So, for example, the GMRT, it works in the low frequency part of the radio spectrum, going
Mhm.
from about 100 megahertz to 1450 megahertz. Then there are other radio observatories in the world which work at slightly higher parts of the radio frequency spectrum, and so on. Um, uh, Most of these are largely national level facilities. Some are small international collaborations to build these facilities.
Mhm.
But if you want to build something that is the next step, much bigger than these facilities like the GMRT and the VLA and so on,
Mhm.
then you need many countries to come together to pool
Mhm.
the resources, both in terms of the financial resources, because it's much more costly to build these much bigger facilities, as well as their technological resources and their understanding, the knowledge, and the expertise. And so this is happening to a large extent in many of the large astronomy projects, and radio astronomy is no exception to that. And the Square Kilometre Array is one of these initiatives where now of the order of a dozen countries have come together to collaborate and build this next generation facility. And so both India and Australia are part of this collaboration. In fact, Australia is going to be the host country for one part of the Square Kilometre Array. The low frequency part of the Square Kilometre Array will be located in Western Australia.
Mhm.
The mid frequency part of it will be located in South Africa. The global headquarters are in the United Kingdom. And the different countries are contributing at different levels to the project, bringing in their knowledge, expertise, and the interest of the astronomers to be able to use this facility for cutting edge science when it is ready.
Yeah. And just last question, Dr. Gupta, where do you see the India-Australia collaboration going in terms of space technology and in this area? I think there's quite a lot of collaboration that has been happening, but where do you see it going in the future? Do you think it's going to get more close as we move forward?
I definitely think so. As you said, there's already been a good amount of collaboration. There is a facility called the Murchison Wide Field Array Observatory, located in Western Australia, in the uh, part of Western Australia, very close to where the SKA low frequency telescope will come up. It's actually called a precursor to the SKA. This was again international collaboration where a few different countries collaborated to build MWA, and India was part of the collaboration. And so there was a good collaboration between India and Australia, as well as some of the other countries that participated in the building of the MWA array. And in the same manner, some of these collaborations have continued in different aspects of astronomy. And between scientists who are using these facilities today to do science, there's again very good collaboration for scientists from Australia and India working together to use facilities like the GMRT and the MWA and others for carrying out the best research that is possible. And going forward, the SKA definitely provides an excellent platform for further closer collaboration between India and Australia on various aspects. So I certainly see this as a partnership that will only grow in strength over the years to come.
Dr. Yashwant Gupta, thank you so much for joining us. And there's a National Science Week going on in Australia. Thank you so much.
Yeah, thank you. It's been a pleasure to be part of the National Science Week of Australia, and good wishes to all Australian colleagues.
Thank you.